All right, so we're gonna move on this morning then into talking about colligative properties. Now, the purpose of colligative properties are to try to give us an explanation for why solutions behave slightly differently than the solvents that make up the solutions do on their own. And in part, this has to do with just a phenomenon of mixing. So we talked already about entropy and entropy increasing when we mix two substances together. Um, but what we also can talk about is that in the process of this mixing, we are also creating different and stronger intermolecular forces. And those intermolecular forces do have a tendency to um, play out. They have a tendency to make things appear different and are functionally different in property compared to what the individual substances were on their own. And so the first one that we're going to look at this morning is something related to vapor pressure. Now, we talked about vapor pressure in Chem 1. So remember, vapor pressure is the natural tendency of a liquid to evaporate. And when a liquid evaporates, if we were to cap that evaporated liquid and measure the pressure of it, that would be its vapor pressure. Well, what we see is that if we go away from just looking at a solvent and looking more at a solvent as part of a solution, we see that there is a definitive relationship between the overall vapor pressure it exhibits on its own and what happens to that vapor pressure when we start mixing it with something else. So this graph is a graph of um, some sort of volatile solvent B and its mole fraction. So here at mole fraction 1, we have pure B. This is what we would call its vapor pressure normally. And what we can see is that as we add some other things to it, as the mole fraction of B decreases, so does its vapor pressure. And the relationship here is a relatively simple one. The pressure that we are seeing for B is related to the mole fraction of B multiplied by its normal unsolution, just itself, vapor pressure. This relationship is known as Raoult's law. So Raoult's law tells us that the vapor pressure of a solution is going to be equal to the vapor pressure of the solvent by itself relative to how much solvent is actually there. The more solvent that is present, the more the solution is going to behave like the solvent does normally. The less present it is, the less it's going to behave like itself. And the more it's going to see that vapor pressure coming down. And the primary reason for this vapor pressure lowering is the increase of intermolecular forces. As we add more intermolecular forces, that solvent is less likely to evaporate because it has other things that are pulling on it and keeping it in the solution. Now, when we add volatile solutes to each other, it does get a little bit more complicated. The vapor pressure of the solution is the sum of the individual changes in the vapor pressure for the components. So if I have two volatile components, A and B, what I will see is that since A has a vapor pressure and B has a vapor pressure, and both of them are going to be impacted by each other, the total vapor pressure that we see is going to be the sum of the two affected vapor pressures. So basically, I have to apply Raoult's law twice. So once for solute A, and then again for solvent B. And naturally speaking, what we would find is that the more that this happens, it would be more of the same. So if I added a third volatile solute, then I would be doing A plus B plus C. If I added a fourth, I'd be doing the sum of those four. Basically, Raoult's law applies to the individual volatile substance. And then our job in terms of defining the vapor pressure of the solution is to add together all of the vapor pressures of the individuals. This sounds a little bit familiar to you. Think back to the end of Chem 105. In the gas laws, we talked about Dalton's law of partial pressures, which said that the pressure of a gas mixture was just the sum of the individual pressures of all the individual gases that make it up. This is no different. Raoult's law tells us how to calculate the individual pressure of a solvent or a solute. If I want to figure out the vapor pressure of the solution, I just need to add together all of the parts that vaporize. And Raoult's law tells me how to calculate the vapor pressure of each individual component. So let's take a look at an example. Maple syrup is produced when sap from maple trees is evaporated until the concentration of the sugar, which is mostly sucrose, reaches to at least 66% by mass. What is the vapor pressure in atmospheres of a 66% solution of sucrose at 100 degrees Celsius? And we can assume that this solution obeys Raoult's law. So first thing that we have to answer for ourselves, is sugar volatile? Does sugar evaporate? No, no, it wasn't a trick question. The answer is no. Okay, so since it's not, this is we're calling this a two-component solution. It's sucrose and water. Do we need to account for the vapor pressure of sucrose? No, because it doesn't have one. But we do have to account for the vapor pressure of the water. And so what this is saying is, okay, the pressure of our solution is going to be equal to the mole fraction of the water multiplied by the normal vapor pressure of water at 100 degrees Celsius. Now we're going to have to look up that value. But luckily, the internet usually has some decent places where we can look for that stuff. Let's solve the mole fraction portion first. If I have a 66% solution of sucrose, so that means I have 66 grams of sucrose. Its molar mass is 342.3 grams in 1 mole. So 66 divided by 342.30 to two significant figures is 0.19. And 34 grams of water would be the result, what's left over. (18.02 grams of water in 1 mole. 34 divided by 18.02 is 1.9. I add those together. I would have 2.1 moles of solution. So to find mole fraction, 1.9 moles of water divided by 2.1 moles of solution. That's our mole fraction. Our vapor pressure, we're going to have to look up. I do not have that one at the ready. And we're looking for the vapor pressure of water at 100 degrees, which according to this website, which is referencing Lang's handbook, which is a pretty good source, 658 is the vapor pressure there. Pour and millimeters of mercury are the same thing. (1.9) divided by 2.1 times 658 to 2 sig figs is 600, 6.0 times 10 to the second millimeters of mercury. And so right away, we would have 2 problems here effectively. If you are in the sugar shack making this maple syrup, you need to turn your boilers back, your heat on a little bit higher. If you remember our definition of what boiling is when vapor pressure meets atmospheric pressure. Atmospheric pressure ranges between 750 and 760 millimeters of mercury. This solution is currently at 600. So we got to raise the temperature to get it up to where it needs to be. So that you can continue to boil this off if you're actually trying to create a more concentrated solution here. All right, any questions about any of the steps here in this process? So what we're going to find is that kind of across the board here, when we're doing vapor pressure lowering kinds of calculations and examples, converting all of the components to moles and finding mole fractions is going to be kind of at the center of most of the work that we do. Let's take a look at an example where we've got 2 solutes, 2 things that are volatile. So we've got a solution that has 100 grams of water and 25 grams of ethanol. And we want to know what are the mole fractions of each of them, and then what is the vapor pressure of the solution. Vapor pressure for water is 23.8. Vapor pressure for ethanol is 58.7. So starting with the mole fractions, we need to convert our 100 grams of water into moles. Molar mass of water is 18.02 grams. So 100 divided by 18.02 to four significant figures is 5.549. And then for the ethanol, 25.00 grams of ethanol. And we want to convert that as well. Molar mass we're given 46.08. So 25 divided by 46.08. Again, four significant figures, 0.5425. So to find the mole fraction, I need to first add. So total moles, 5.549 plus 0.5425. We've got 3 decimal places here and 4 here, so we need to round to the fewer, which is 3 decimal places total. So 6.092. So the mole fraction of water would be 5.549 moles divided by 6.092 moles. 5.549 divided by 6.092, 0.9109. Now I could do that same fraction calculation with the mole fraction of ethanol, or like we talked about before, recognizing that it's the other part of this solution and that all things have to add up to 1. I could get the mole fraction of ethanol as 0.0891 that way. Find the vapor pressure of the solution. I basically just have to apply Raoult's law to each component. So I need the pressure of the water and the pressure of the ethanol. For the pressure of the water, it's the mole fraction of the water and its vapor pressure. And then the same thing for the ethanol. Its mole fraction times its vapor pressure. Plugging in my values, 0.9109 for the mole fraction of water and the 23.8 torr that they gave me for the vapor pressure. For the ethanol, the 0.0891 and the 58.7 torr that they gave me for that. .9109 times 23.8 gives me 21.7 torr for the water. 0.0891 times 58.7 gives me 5.23 torr for the ethanol. I add those two together to one decimal place. We get 26.9 torr as the vapor pressure. And what you'll always find in cases like these, when we have just one volatile component, the vapor pressure always drops. When we have multiple components, what we're going to see is that the vapor pressure is going to shade toward the one that is the greatest, in the greatest supply. So with water being over 91% of the moles in that solution, it should come as no surprise that the vapor pressure of the solution is heavily favoring water's vapor pressure as opposed to ethanol's. And what we'll always find also is that in these two component systems, basically what we're doing is a weighted average. That's basically what we're doing. The value is going to come between the two goalposts. Whether it's between the one or the other really comes down to what the mole fractions are. The more evenly distributed the solution is, the more it's going to be like right down the middle. But like we see here, with a solution that's 91% water, it favors the water. It's a weighted average there. All right, any questions? All right, try this one then. We've got 0.2 of a mole of glucose being added to 0.2 milliliter or 0.2 liters, 200 milliliters of water. By how much does the vapor pressure decrease? All right, we had to add a couple of details here to help us out. So we're talking about boiling water here, which means that the vapor pressure is equal to atmospheric pressure, which we're just going to assume is 1 atmosphere, 760 torr. So what we need to do then is we know how many moles of glucose there are. What we're trying to figure out is what is the pressure of this solution. So we need to know the mole fraction. Well, we know how many moles of glucose there are. How many moles of water are there in 200 milliliters? Well, here's where we're gonna have to make an assumption. The assumption is that 200 milliliters is 200 grams. Density of water is 1 gram per milliliter. And if we convert the grams here into moles, 200 divided by 18.02, we will get 11.1 moles. So if I add the 0.2 moles of glucose to that, that'll give me up to 11.3 moles. And so this solution, 11.1 divided by 11.3 times 760 to three significant figures is 747 torr. And so the change in pressure would be, we started at 760, we're now at 747, it'd be roughly 13 torr, which is closest one to that is letter B. So yeah, without some of that extra information there, this question's pretty much impossible to answer. It happens sometimes, right? Aside from the normal confusion of not being given enough information to solve the problem, now that we have solved the problem, are there any questions? All right, let's try this again then. This is a question I wrote, so I've already done it. I know it has a correct answer. We've got a solution that has 100 grams of water, 25 grams of sodium chloride. What is the vapor pressure of the sodium chloride solution? And sodium chloride is not volatile, so we don't have to worry about that. Uh, the question in the PowerPoint is missing something that is not in the that is in the top hat version. The vapor pressure at normal conditions is 23.8 torr. So if that's the data point you're looking for, it was in the top hat one, but Okay, so the process here, you can take this a couple of different directions. But what we're since sodium chloride is not volatile, then we don't need to calculate Raoult's law for it because it doesn't evaporate. So the pressure of the solution would just be equal to the pressure of the water, which would be the mole fraction of the water times its vapor pressure, which is 23.8. The only thing we're missing is we don't know what the mole fraction is yet. So with 100 grams of water, we need to convert that into moles, and we get 5.549. And the 25 grams of sodium chloride, we need to convert that. So 25 divided by 58.44, we get 0.4278. So adding those together, 5.977 moles. So for mole fraction, 5.549 moles of water over 5.977 moles in total, multiplied by the 23.8 torr. And we're going to get a pressure of solution uh, 22.1 torr. Now, I was talking about this with one of you. If you happen to do the Raoult's law for the wrong thing, so you make the mistake of doing Raoult's law on the solute that doesn't, the thing that doesn't evaporate and not the thing that does, you're not actually in trouble. Because if you do that, what you've actually calculated is how much the vapor pressure goes down. So, we did that calculation. We ended up getting 1.7 torr. And you're like, oh, what do you do with that? Well, you just figured out the difference. So you can still solve this problem. 23.8 minus 1.7 is 22.1. That's the correct answer. So if you make a mistake like that, it's not the end of the world. It's actually, you just found a different way to solve the problem. You figured out the difference instead of the pressure. And in a case like this, it doesn't matter. You're trying to figure out the problem anyway. In some ways, you had to figure out what the difference was to begin with. So questions about this? Okay, so Raoult's law describes what we would call ideal solutions. That is, solutions that are going to generate results that are predictable according to Raoult's law. But that assumes one thing. That assumes that the intermolecular forces that are being generated in that solution are actually behaving ideally. And so when they don't behave ideally, what we'll see are some deviations from Raoult's law. And so these dotted lines here, the dashed lines here, where we see higher than expected vapor pressures, these are the results of weaker interactions. So if the interactions between the solute and the solvent are weaker than expected, weaker than the solvent, the attractions between the molecules in themselves, we're going to see that the vapor pressure ends up being higher than we expected. And if we end up having stronger interactions, then we're going to end up getting even better vapor pressure lowering because of the strength of those interactions. Now, I'm not telling you this because the next thing I'm going to show you is a calculation for how to correct for this. It isn't. It's just to tell you that Raoult's law is based on what we would call ideal behavior. But if we deviate from ideal behavior, we can expect either a greater lowering because of increased intermolecular force or a lesser lowering because of decreased intermolecular force. So to put things kind of away for the day, there's no top hat question for this. I just want to kind of get you thinking a little bit, and this will put us in the mode for finishing up colligative properties tomorrow. And so to that end, assignment 18.2 on colligative properties, other than Raoult's law and maybe the beginnings of some of this freezing point, boiling point stuff, we're not going to really see much of it today. We took a little bit longer going through the Raoult's law stuff than I had anticipated. But I want you to kind of think about this to get us framed up for what tomorrow is going to look like. Knowing what we know, especially having talked about it today, looking at pure solvent versus solution. We talked about the idea of vapor pressure lowering. How does this idea in general, how would it apply to things that are also related to intermolecular forces, like freezing point or boiling point? Maybe we should start with that bottom question, because that one's probably the most directly related to what we were just talking about. How would we expect the boiling point of a solution to change relative to the pure solvent? Put it in the context of Raoult's law. With increasing solute concentration, what happened to the vapor pressure? Vapor pressure wouldn't increase with concentration. It would decrease. They're inversely related. So my concentration is going up, my vapor pressure is going down. Now, what's the relationship between vapor pressure and boiling point? What's the definition of boiling? Vapor pressure has to match atmospheric. Okay, so if the solution is bringing down my vapor pressure, is the atmospheric pressure changing? No. So what do I got to do to this solution to get its vapor pressure to come back up to where it needs to boil? What do we do to things to boil them? We heat them. Yeah, we raise their temperature. Okay. So if we've lowered the vapor pressure, not only are we going to have to heat it the normal amount, we're going to have to heat it extra to get it up to the proper value. So what does that mean for boiling point? Well, if we have to heat it extra, boiling point is going to go up in some way. Now let's apply this to freezing. This one's just kind of think about it more intuitively. If a solution causes things to stay liquid longer because they're changing the dynamics of the solution, what does that mean for turning into the solid phase? It's going to have to lose more energy to freeze. So the freezing point is going to drop, just like the boiling point had to spike. What does a solution do? A solution basically does, through mixing, through intermolecular forces, it allows a liquid to be a liquid for longer because the forces that exist in that liquid are stronger than the solvents themselves. Because think about it, when we boil salt water, is the salt going up into the solution with the water? No, it's staying behind, which means we're really looking at the water itself, right? The water is staying in that liquid longer. And the reason it's staying in that liquid longer is because the salt particles are saying, I gotcha. Let's stay together. We have a stronger force. Well, that same logic applies on the low side of things as well. Because when you freeze a solution, it doesn't freeze all at once in one glob. The solvent freezes first. And if you continue to remove heat, then the rest of it freezes as well. That's how popsicles work. But if I don't get it down far enough, even something as simple as a popsicle could separate, and we would have an ice component and a non-ice component. And you see this a lot. Think about what freezer burn is. You ever get a bad scoop of ice cream? It's got all that gritty ice in it. Well, if it doesn't freeze fast enough, the water molecules inside of that ice cream freeze first, and they jag up the whole mess. And so everything freezes around it. You get little ice crystals inside of your ice cream instead of that smooth, creamy ice cream. So it works on both ends of the spectrum. The concepts, and we'll talk about these starting tomorrow, are what are called boiling point elevation. That is the raising of boiling point because of the lowering of vapor pressure caused by intermolecular forces inside of the solution versus the solvent by itself. And freezing point depression, the other side of the spectrum, where solutions are going to freeze at lower temperatures than their pure solvents because of those same intermolecular forces that are keeping them together. So that is where we will end for today.